T is equal to Ts at R is equal to. So here, can we actually integrate it casually? We cannot actually integrate it regularly. The issue is that it is actually because T is actually coming out here. Okay. So if you actually see the previous equation, whenever we actually went for the constant heat flux, okay, constant heat flux, on one side we were having all the constant values, and the other side we were having all the variation along the R. Okay, for example, what we said is the equation what we actually got was 2 1 minus R by R0 square dTm by dx equal to alpha 1 by R dou by dou R of R dou T by dou R. This was actually the equation we actually got for a constant surface heat flux. Yeah, constant surface heat flux. But for the constant temperature condition, we can actually see that there is actually this T term also comes on the RHS. Okay, so because of that, this RHS side, it is actually not constant along the not constant at any particular x. Okay, even if we are actually going for a particular x, we cannot actually integrate it analytically. Okay, so therefore we have to actually solve it numerically. Okay, we can actually go for some shooting method, etc. You can actually go for. So we have to actually solve it numerically. Okay, can solve numerically. Okay, to get, so our ultimate aim is to actually get the Nusselt number. N is equal to 3.66. Okay, so 3.66 is the Nusselt number that we are actually going to get. Okay, we can actually call it 82. So this 3.66 is the Nusselt number for it. What was the Nusselt number for constant heat surface flux? It was actually 4.36. Okay, so here you can actually see that the Nusselt number is actually higher for the constant heat flux condition compared to that of constant surface temperature. Okay, so if you actually draw it along the length, okay, draw it along the length, you can actually see that for one condition, it is actually going to be this is a 4.36. This is actually Q is equal to heat flux is equal to constant condition. So likewise here also initially it might be actually going to be different. Okay. So once the fully developed region is actually going to be there, it is actually going to be constant. This is actually going to be constant. This is 3.66. 3.66. So this is for Ts is equal to constant. Okay. Yeah. So this is actually going to be the case. So at any in the fully developed region, we are actually talking about a fully developed region over there. In the fully developed region, so therefore we can actually see that the heat transfer coefficient is actually higher for the constant heat flux condition. Okay. So if you are actually drawing the therefore if you are actually going for this temperature profiles and all, it is actually going to be higher for the gradients are actually going to be higher at the wall for constant surface flux condition. Okay, because we in between we actually derived non-dimensional Nusselt number is equal to dou T by dou xm, right, in the boundary layer region. So therefore, this is actually what we can actually take away from here. But again, one more issue. Yeah, this is actually main. So once we actually have any flow through pipe, okay, so you need to actually see what is actually the boundary condition. And if you want to have a heat transfer at any particular location, okay, so you have to actually calculate the mean temperature. Okay, if we are having some thermocouples, you can actually measure that, and we actually know what is actually going to be the H because the lamina flows till to Reynolds number less than 2000. Okay, so till Reynolds number less than 2000, we can actually take that for a constant heat flux condition. It is actually going to be 4.33, the Nusselt number. Corresponding to that, we can calculate the heat transfer coefficient. And again, for constant surface temperature, it is going to be 3.66. Okay. That is actually going to be the case. And again, in some cases, what we are actually more interested is actually the total heat transfer. Okay. So total heat transfer, it is actually going to be important. So total heat transfer, if you are actually saying total heat transfer, say heat transfer for constant heat flux, constant Q condition, there are actually two ways in which we can actually do. So we are actually saying Q flux is equal to constant. So the total heat flux, say Q, we can actually say heat flux into pi d into L. This total surface area that we can actually do. Okay. So if you are actually saying, I just want to find what is actually going to happen in the fully developed condition. Okay. So we can actually say Q transferred in fully developed. So that also we can actually find from the area. We have to actually check only the fully developed surface area. Otherwise, we can actually go for H into area or heat flux. Yeah, H into A into, we can actually say Ts minus Tm. Okay. At a average, we can actually say a mean of Ts minus Tm, because we said that the Ts minus Tm in the fully developed region, it is actually going to be constant throughout. Okay. So T minus Tm, so therefore anywhere you are actually going to check, it is actually going to be same. So therefore we need to actually calculate what is the total heat flux, and then you can actually find it. Okay. So in a total constant heat flux condition, calculating the total heat flux is actually going to be very simple. Okay. So with the logic itself, we can actually going to find it. But for a constant surface temperature condition, it is actually not going to be that simple. Okay, so we need to actually go with something called as log mean temperature difference. Okay, so that's what we are actually going to see now. Log mean temperature difference. Okay, log mean temperature difference. So why we are actually doing is because for constant surface temperature condition, okay, constant surface temperature condition, it is actually approaching the Ts exponentially, as we said. So this is actually Ts and this is actually Tm. Okay, this is actually in x direction, and this is actually temperature. So therefore, it is important for us to calculate the heat flux. Okay, so Q total heat flux is equal to H into surface area into delta T. Okay, so we need to actually see what kind of delta T we need to actually see, because we cannot actually simply go for an average delta T. If you are actually saying, say, I'm actually taking the delta T at the center, is that actually okay? We cannot actually go for, because there it is actually, if it was moving linearly, then it was actually still okay. But here it is actually not moving linearly. So we need to actually come up with something which is actually going to make sense. Okay, so that delta T is actually going to be the logarithmic. We have already seen it when we actually discussed the flow over bank, but we are actually going to derive and see how it is actually coming out. Okay, so here, so we are actually starting with a dTm by dx. Okay, so this we actually already said dTm by dx is equal to P into H into Ts minus Tm divided by mc. Okay, mcp. So dTm by dx is at a particular section we are talking about, right? For a particular section, or here itself. Here itself we can actually see what is actually dt by dx at this location. So at this location we can actually say Ts minus T. So we are having trouble when we are actually talking about the overall average. Okay. So but dt by dm, so we are actually going to write it like say minus of, or we can actually say dTm by dx. We are actually going to write as minus of d of Ts minus Tm divided by dx. Can we actually write it like this? Is that okay? It is okay, because dTs by dx is actually going to be equal to 0, because this is actually constant surface temperature condition. Okay. So from these two, we can actually write as minus dTs minus dm Tm divided by dx equal to pH Ts minus Tm divided by mc. Okay, so this one you can actually write 82 point there. So now we are actually going to integrate it. So we are actually making the like terms and combining the like terms, and we are actually going to integrating it. Integrating from inlet to exit. To exit. Okay. We are actually trying to say here, we actually said for a small section, we actually said Ts minus Tm. So we are just going to see if we are actually integrating, anything will actually come out. We are not sure, we can actually just see. But x is equal to 0. So therefore, integration means Ts minus Tm at inlet. Okay, we can actually write as a delta T, okay, where delta Ti. Okay, so also at x is equal to L at the exit, we can actually write Ts minus Tm outlet, which is equal to T0O. Okay, where we can actually write delta T is equal to Ts minus Tm. Okay, so you know that here Ts is actually going to be constant throughout. Only the Tm is what actually varies along the length. Okay, so now we are actually going to integrate it. So delta Ti to delta T0. So where we are actually integrating d into delta T. Okay, so this is actually d into it. So this one we are actually writing therefore minus of delta T by dx is equal to pH delta T by mc. Okay, so this is what this equation is. So divided by delta T is equal to minus P by mcp integral 0 to L h dx. Okay. So this is actually going to be the equation. So this is a simple integration. We can actually integrate it. So if you are actually going to integrate, we are actually going to get ln delta To divided by delta Ti is equal to minus P by mcp. Okay, we are multiplying and dividing by L, 0 to L h into dx. Okay, but we know that h bar is equal to 1 by L integral 0 to L h into dx. That we already know, we have actually derived it long back. Okay, so therefore we can actually write ln delta T0 divided by delta Ti is equal to minus PL by mcp h bar. Okay, so this is actually one big equation. So 82.c we can actually write. Okay, so this one you can also write as, if you are actually going to take the exponential, delta T0 by delta Ti is equal to exponential of minus PL by mcp into h bar. Okay, so if you remember, this is actually what the equation we actually wrote for delta To by delta Ti for banks. Okay. Did we actually write here? I think it is here already. Yeah, here itself. Here itself it is there. If you remember, for flow over cylinders, flow over multiple cylinders, a bank of cylinders, we actually wrote the same equation, exponential of minus as h by mc, right? Yeah, the same equation over here. P into L is perimeter into length is obviously going to be equal to surface area. Okay. So we are not going to stop over here. We need to actually have a delta T as it is. We are not want to different terms of delta T or delta T. Okay. So therefore, total heat transfer, we can actually say Q is equal to mcp Tmo minus Tmi. Okay. So we are writing it in terms of the change in energy of the fluid, because whatever the heat transferred, it is actually going to be taken by the fluid only. So therefore, its temperature changes from Tmi to Tmo, right? So that is actually the total energy being received by the fluid. So we are just going to change it. Okay, so we are just desperately trying to see what is actually going to be the TS. So this one, this basic equation, we are actually going to add and subtract by TS. Okay, add and subtract by TS. So therefore, we are actually going to write TS minus TMI, okay, minus TS minus TMI. Okay, so this minus minus actually becomes a TMO becomes a positive, and negative TMI is actually going to be. So this is actually going to be the same. But if you're actually going to write it like this, we can actually write as delta Ti minus delta To. Okay. So Q is equal to MCP delta Ti minus delta To. Okay. So what we want to actually use is what is actually going to be the MCP. So therefore we can actually write MCP is equal to Q by delta Ti minus delta To. So that's what we want, because in our equation over here 82.2 we are having this MCP. We are just trying to remove that MCP from the equation. Okay. So this is actually yeah. Okay. So this is actually going to be putting MCP in what is the equation above 82.c. Okay. 82.c you are actually going to get I'm sorry, we have to actually write MCP from here. Okay, or equate the MCP from here. Okay, so we are actually taking MCP off from here because we need to actually have Q in our yeah, both are actually going to be the same, right? Both are going to be the same. Okay. So what we are actually going to get basically is Q convection is equal to HAS, where AS is equal to P into L. Okay, HAS into delta TO minus delta TI divided by ln delta TO by delta TI. Okay, so this one you can actually write as HAS Q is equal to HAS delta T ln. Okay, so this is 82.D. So where delta T ln is equal to delta T0 minus delta Ti divided by ln delta T0 by delta Ti. Okay, is log mean temperature difference. Log mean temperature difference. So this is actually a mean temperature only, but it is actually used a log term for average heat. So this is actually the appropriate average temperature. Okay, average temperature due to exponential variation. Exponential variation of Ts minus T. Okay, so this is actually the appropriate average temperature due to exponential variation of Ts minus T. Okay, so that is actually going to be the log mean temperature difference. So whenever the temperature is actually going to be any temperature is actually going to be constant, we need to actually follow this log mean temperature for the further analysis. Okay. Yeah, so this log mean temperature difference that we will again see when we are actually talking about surface heat exchanges, because there also even though it was actually not constant surface temperature, this log mean temperature will actually come when we are actually talking about counterflow heat exchangers. Okay, so whenever we are talking about counterflow heat exchangers, then the temperature variation are actually going to be something like this. Okay, so those things we will actually see later. So there also we will be actually coming up with log mean temperature difference. Okay. So any doubts in here? So from the convection part, from the forced convection part, we have therefore seen initially the boundary condition, then we actually saw the further analysis, and then we actually saw the boundary layer approximation, then Reynolds analogy we actually saw. Okay, then we actually saw the flow over flat surface, then we actually saw flow over cylinders, bank of cylinders, then we actually for internal flows, we actually saw that for constant surface temperature as well as the constant heat flux conditions. Okay, so with this basis, you can actually explore to other levels also. Okay, so whatever the basic conditions we have already seen, external flows as well as the internal flows we have actually seen already. Okay, based on this, you can actually explore to anything else. Okay, yeah. So that is yeah. So that's what I wanted to mention from this uh, internal convection or the forced convections. So now we are actually going to see free convection. Okay. So now we are actually going to see free or natural convection. Okay. Free or natural convection. Can anyone say any example for a free or natural convection? Anything? An example for free or natural convection, which is occurring in nature. Can anyone say any example? Any
Warm air,
example?
sir. Flowing
Which
of
one?
warm air. War,
Which one?
flowing of warm air, sir.
Moving of warm air. Yeah, in a
Sea
sense, we
breeze
can
and land breeze, sir.
yeah, very good, very good. So this breeze, this wind, that is actually natural convection. Very good example. Okay, and also if you are actually going for boiling a water, okay, so you can actually see this boiling is actually before that you can actually see that the internal itself when you are actually before the boiling of water, there is actually going to be some internal circulation within the fluid. So that is actually going to be boiling. That is actually something which is actually happening within without any external forces. Okay, without we are actually applying external energy. So those are actually the free convection. Okay, yeah. So without a further introduction, we can actually directly go. We can actually write as convection process. Convection process without the aid of external agents. External agents like agents like fan or blower, but happens naturally. That happens naturally naturally because of temperature dependent density gradient. Dependent density gradient. Okay, is called free or natural convection. Free or natural convection. Okay. So what happens is that suppose if you are actually going to have a if you're actually going to have a hot body or something, okay, if you're actually going to have a hot body or something, okay, it is actually say hot body. So this is actually a hot object if we are actually seeing. It is a hot object. And what happens is that uh, hot fluid is actually going up. Okay, hot fluid, will be actually going up. Over here, the surface, the region or the air near to it is actually going to get heated up and it is actually going to go up, right? It is actually going to go up. And to that place, cold air comes. Okay, so cold air comes. So this is actually the red is actually the hot air okay, hot air, and this is actually the cold air. Cold air. Okay. So therefore, you can actually see the hot air is actually going up and cold air is actually coming out. Whereas if you are actually going for a cold object, okay, if this is actually a cold object, it is going to be cold object. So then what happens is that uh, again further cold body, cold fluid is actually going to come down. Okay, so whatever it is actually getting cold, it is actually going to come down. Okay, it is actually going to come down, and whereas relatively hot fluid is actually going to come out. Okay, hot air, and this is actually cold air. Okay, so that is actually going to be this natural convection. So here we are not giving any external forced movement of the fluid, but because of the internal forces itself, it is actually going to. But why it is actually going to happen? So what is the main force that is actually going to happen over here? Can anyone say? What is the force that is actually happening? Or if you are actually not giving in externally, but internally some energy is actually going to happen. What is that energy? Or what is actually that force? It is the, what is that force? Anyone, can anyone say?
The buoyancy.
It is a, yeah, very good. It is actually the buoyancy force that is actually going to force this. Okay. So you can actually write yeah. So density, the density of gas, density of gases and liquids depends on temperature. Density of gases and gases and liquids depends on temperature. Generally decreasing with increase in temperature. Decreasing with increase in temperature. Increase in temperature. Okay, temperature. We can actually write d rho by tau t is less than 0. Okay. So we know that whenever there is actually going to be a fluid, okay, and if you are actually going to dip any object of a different density, what is actually going to happen? There is actually going to be a force over this body, which is actually, or there is actually going to be upward force onto the body, which is actually equivalent to the volume of fluid which is actually displaced. Okay, so that is actually the buoyancy force acting on that. So here, instead of a different body, what we are actually going to say is, if you are actually going to place this hot object over here. So initially, this much place, okay, we are actually having this hot body. So initially all these places were actually uh, given by this cold fluid. Cold fluid in the sense it is actually the fluid which is actually of ambient temperature. Okay. Suddenly you are actually going to heat it. So particle over here, it is actually going to increase its temperature. Okay. So particle over here, it is actually going to increase its temperature. So therefore, what happens if the temperature is actually increasing, its density is actually going to reduce. Okay. Whereas the fluid over here, the fluids which are actually outside, it is actually having still higher densities. Okay. Still higher densities it is actually going to be. So therefore, these lower density fluids, they are actually going to experience a buoyancy force. Okay. And it is actually going to experience a buoyancy force. So therefore, it is actually going to go up. Okay. Because of the buoyancy force, it is actually going to go up. Okay. And the cold fluid therefore comes to take its place. The cold fluid is actually therefore comes to take its place. So in here, what we actually said is the buoyancy force, that is actually the force corresponding to the weight of the fluid displaced, right? So what is actually weight? Weight is equal to mass mg, right? Mass into the gravitational force. So this is actually the acceleration due to gravity, right? So because of the gravitational force, we can actually say it is actually going to take up. Okay. So therefore, this density differences along with the body forces is what going to be. Here the body force is actually going to be due to the gravitational force. Okay. So let's see one more case. Suppose I am actually having a fluid over here, something like this. Okay. Or simply say, um, okay, simply say, I am having say a mixture of hot fluid and cold fluid. Okay, a mixture of hot fluid and cold fluid. Okay, we can actually say some immiscible fluid or something. A mixture of hot fluid and cold fluid is actually over there. Just assume. Okay, so just assume that mixture of hot fluid and cold fluid is actually going to be there. Okay, so here also, even though density is actually going to be there, so together with that, what we are actually going to do is we are actually going to rotate this. Okay, we are actually going to rotate this in its axis. Okay, so then here what is actually going to be there? So in addition to the gravitational force, there is actually going to be centrifugal force. Okay, centrifugal force, again it is actually going to give centrifugal force is equal to mass into acceleration due to, we can actually say, centrifugal force. Okay, mass into acceleration due to centrifugal force. Okay, so therefore here also we can actually see that the cold fluid, it is actually going to have a higher mass, right? It is actually going to be having a higher mass. So therefore, it is actually going to be accumulating towards the exit. So it is actually going to experience a higher force. So after the rotation, if you are actually going to see, after the rotation, if you are actually going to see, then you can actually see that all the cold fluids might be actually accumulated towards the wall, whereas the hot fluids, most of them are actually accumulated in the center region. Okay, why? Because here the force we have actually used is centrifugal force. Okay, so because of the centrifugal force, okay, so now the centrifugal force is actually acting as the body forces, and because of that there is actually going to be a gradient. Okay, so whenever this was actually happening, so like we are actually seeing it out here. So like we were actually seeing it out here. Okay. Yeah, suppose if you are actually going to heat, if you are actually going to heat the walls, if you are actually going to heat the walls, if you are actually going to heat the walls throughout, I think that is actually a better example. If you are actually going to heat the walls throughout, if you are going to heat the walls throughout, then what happens is that the walls towards the temperature of the fluid, which is actually near to the wall, it is actually going to have a lower densities. Okay, so by the time the center fluid, it is actually going to get cooled out. Okay, so therefore, then it is actually going to be the center fluid or the fluid in the center region, it is actually going to have a higher masses, and therefore it is actually going to be thrown out towards the center. And whatever the hot fluid near to the walls, it is now having a lower density and it is actually going to get in. Okay, I think that is actually the better example. Okay, let me explain again. Yeah, here we are having some hot surfaces, higher temperatures. Initially, we are actually filling up with fluids. Okay, initially we are filling up with fluids. Okay, what happens is that towards the wall, obviously the temperature of the fluids are actually going to increase. So hot fluids are actually going to be over here. Hot fluids are actually going to be over here. Okay, so now if you are actually going to rotate our cylinder or rotate our pan, then what happens is that since the hot fluid actually having a lower density, okay, and here the force is actually going to be there. There is actually going to be a force as of centrifugal force that is equal to mass into centrifugal acceleration. Okay, and here you can actually see that the cold fluids are having a higher density, therefore it is actually having a higher mass, higher forces. Okay, so therefore what happens is that the cold fluids, cold fluid is actually gone over here, okay, and hot fluid will be actually coming like this. Okay, so here you can actually see that again this buoyancy force is actually comes into picture, but here instead of the gravitational force, we are actually going to have the centrifugal force. Okay, yeah. So any kind of body forces, so we can actually explain it for the Coriolis forces also, whenever it is actually orthogonally rotative, then also we can actually go for this kind of explanations. Okay, so it is not just because of the density variation, but density variation together with the body forces. So that's when this buoyancy force going to happen. Okay, we said that density is actually going to be there. So when body forces, we can actually see in the bracket such as gravitational, or centrifugal, or even Coriolis forces. Coriolis force. Okay, when body forces such as gravitational, centrifugal, or Coriolis forces acts on a fluid, with density variation, with density gradient, net effect is buoyancy force. Net effect is buoyancy force. Okay, buoyancy force which induces free convection, Okay, so that is actually the reason by which we are actually going to have the natural convection. Okay, so natural convection can be actually occurring anywhere. For example, as we said, if you're actually going for a rectangular enclosure, okay, a rectangular enclosure with say two surfaces T2 and T1, and if you are actually going to have T1 greater than T2, then what happens is that there is going to be a continuous evaporation, continuous circulation, because whenever the surface temperature over here on the bottom wall is actually going to get high up, so from the top it is actually going to come into the bottom. Okay, so we can actually say rectangular enclosure, or if you are actually going to have a hot wire. Okay, if you're actually going to have a hot wire, okay, if you're actually going to have a hot wire, then what happens is that the air over here, air in the vicinity of this, it is actually going to get heated up. Okay, so therefore there is actually going to be a buoyancy force. Okay, but what happens is that as the fluid is actually moving up, it is actually going to entrain some fluid from the outside. Okay, it is actually going to entrain the fluid from outside. So as some amount of hot fluid is actually going up, it is actually going to entrain. Okay, it is actually going to entrain fluid from outside. Okay, so that's why we can actually see this boundary layer is actually developing. So this is actually the boundary layer. So within this, we can actually see that the velocity is actually going to be maximum at the center, and it is actually going to come in and out like this. Okay, so inside density is actually going to be rho. Okay, inside density is actually rho. Here, you can actually write as velocity. Inside the density is actually rho, outside density is actually rho infinity, because the temperature is going to be T infinity. Here again, temperature we can actually write as T. Okay, so here this is actually probably this is actually a heated wire. Okay, this is actually a heated wire, and this kind of a buoyancy, that's it actually known as plume. Okay, and again we are actually going to having a different type of buoyancy, like buoyant jet is actually going to be there. So likewise, various conditions are actually going to be there because of the buoyancies. Okay, So, however, here we are actually going to study for vertical plates. Okay, we are actually going to see vertical plates. So, this is actually one of the simplest one in natural convection. Okay, so if you can actually understand this, then other things we can actually go for later. Okay, so vertical plate is what we are actually going to see over here. Suppose if you are actually having a vertical plate like this. Okay, vertical plate like this, it is actually having a higher temperature, say Ts or some. Okay. It is having some temperature Ts, and obviously its temperature is actually going to be higher than that of ambient condition. So therefore, there is actually going to be generation of a boundary layer. Okay. So here, what happens is that over here at the leading edge, at the bottom edge, the boundary layer thickness is actually going to be very less. Why the boundary layer is actually going to happen is, as and when the hot fluid is actually going to go up, as and when the fluid is actually going to go up, here from here only a very small amount of fluid is actually going up, right? So from here again the fluid is actually going up. Okay, from everywhere some fluid is actually going to go up. It is not from the wall it is actually happening, but over the wall this is actually going to go up. Okay, so as and when you can actually see that at this location, if you're actually seeing at this location, so there is actually so much of current is actually going to be there. Okay, so that's why this boundary layer thickness or boundary layer is actually going to increase its thickness. Okay, and that's why this boundary layer is actually going to be there for the natural convection condition. Okay, yeah. So can anyone say what is actually going to be the velocity profile with it? Can anyone say the velocity profile with it? So suppose if you are actually taking this particular location, onto the wall, what is actually going to be the velocity? Onto the wall, always this no slip conditions are actually going to be there. Okay, and also what can be actually the boundary condition or the velocity at this location? Okay, so this location at the end of boundary layer also, it should be actually 0, but because what is actually boundary condition? Outside we are actually saying the velocity is actually 0. Okay, so this is actually going to be a quiescent surface, okay, where stationary or stagnant condition we are actually taking. So outside the velocity is actually going to be 0. So therefore, at the end of boundary condition or end of boundary layer, the velocity should be actually equal to 0, right? So therefore, if you are actually going to draw the velocity condition, it will be something like this. Okay, so it is actually 0 at the wall as well as it is actually 0 at the boundary line. Okay, so this is actually the boundary layer surface. Boundary layer surface. So this is actually going to be the velocity boundary, velocity condition, velocity profile. Okay, and we are actually saying this is actually the delta thickness, and obviously we need to actually consider the body force, which is actually P. Okay, we are taking our axis such that along the height it is actually going to be x direction, and perpendicular that is actually going to be y direction. Okay, because in we are actually going to analyze the flow in the in the vertical direction. Okay, so just for simplicity, this is just for convenience we are writing x and y. So this is actually the velocity boundary layer. Velocity boundary layer. And
So
what
one
about?
doubt, sir.
Yes, please.
So why is the velocity 0 at the other end of the, I mean, like at the edge of boundary layer? So
If we are actually going for a flow or flat surface, how do you actually define the boundary layer? What is actually going to be velocity at the boundary layer? U by U infinity is equal to 1, or what we are actually saying is U is almost equal to U infinity, right? So whatever the outside velocity. So here what is actually the outside velocity?
oh
It is
yes, sir.
actually static.
Yes.
It is actually going to be 0. Okay. Yeah. I will give you one more example. Suppose if you are actually having a surface like this. Okay. If you are having a surface like this. Suppose if you are actually having a small slot. Okay. If you are actually having a small slot like this. So here fluid is all static. Okay. what you are actually going to do is we are actually going to give flow from here. So flow is actually happening only through this hole. So everywhere else, the velocity is actually going to be equal to 0. Okay. So here also, therefore, we can actually say the boundary layer, it is actually going to develop obviously, and the velocity is actually going to be like this. Okay, somewhere here it is actually going to maximum, and here it is going to be 0. Okay, so boundary layer is actually the condition in which everywhere where the water near to the surface, it is actually approaching the ambient condition. If it is 0, then it should actually approach 0. Then if it is having some velocity, it should actually approach velocity. Okay. Yeah.
Yes, sir. Understood. Thank you.
Yeah. Okay. Fine. No need for thanks. Okay. It is actually good that you are asking. Okay. Yeah. So that is actually what happens for the velocity boundary layer. So now we are actually going for the thermal boundary layer. Okay. So likewise, obviously, the temperature is actually going to be somewhere around Ts. Okay. So here, or here again, what we are actually going to see is at the bottom, the amount of the fluid to which this wall surface or the surface temperature is affected is actually going to be less. Okay. So if you are actually talking somewhere over here, till here, yeah, here you have actually seen this velocity or temperature is actually, or the flow is actually going to happen till to a location delta. Okay. Likewise, at least till that layer, these boundary layer thickness, the thermal effects are actually going to be there. Okay. It can be actually more than that also. It can be actually more than that also. It can be actually less than that also. Okay. But till some portion, the effects are actually going to be there. And you can actually see as we are actually increasing the height, the distance in the fluid from the surface to which these thermal effects have actually penetrated, it actually increases. Okay. So therefore, this is actually the thermal boundary layer, we can actually say. Thermal boundary layer again. So at any location, if you are actually going to draw the boundary temperature profile, so here you can actually see that here the surface temperature, so onto the surface, the temperature is actually going to be Ts. Okay. And it is actually gradually reducing. And it is actually going to T infinity. Okay. So this is actually going to be the temperature profile. Okay. So this is actually Ts and this is actually going to be T infinity. Okay. Yeah. So this is actually going to be the thermal boundary layer. And again, here also we are actually considering the density, and outside the temperature is going to be T infinity and rho infinity is the density. So inside we can actually say rho is actually the, and yeah, rho is actually the density, and this distance, it is actually going to be delta T. Okay, that is actually the boundary layer thickness. Okay, yeah, just a side note, as we are actually discussing on this. Okay, so suppose if you are actually going to have a cold surface, you are actually going to have a cold surface, then it is actually going to be something like this, right? So the fluid is actually going to be, it is having a temperature or velocity boundary layer like this. And its temperature profile, it is actually going to be something like this, right? Or here, the surface temperature is actually going to be less. Ambient condition, it is actually going to be higher. Okay. So what I want to say is this surface temperature or the boundary layer temperature profile, it actually depends upon the relative temperature between the surface as well as the ambient condition. Okay. So here again, our this is actually y and this is actually going to be x. Okay. So this is actually what the temperature and velocity profile, the thermal boundary layer profiles in the vertical plates. Okay. So now we are actually going to see how it is actually going to be. Obviously, we have to actually go with the momentum condition. So governing equations. So this x momentum equation, which is actually the Navier-Stokes equation, whatever we actually derived, it is actually it is all good for here also. Okay, so there we didn't actually say like it is actually going to be forced convection or something. So natural convection, that is actually applicable for any flow conditions. It should be just it should be Newtonian flow. That's it. Okay, it is a Newtonian flow with incompressible. Whatever we derived is for actually incompressible steady state. Okay, but Navier-Stokes, it is actually applying for any kind of Newtonian fluid. So therefore, if you are actually taking x momentum equation, okay, x momentum is now in a vertical direction. Okay, x momentum equation with body forces. Here we need to actually consider the body forces. Okay, body force per unit volume as rho into minus rho into g, because here g which is actually the acceleration, it is actually negative x direction, so we need to actually take it as minus rho into x. Okay, so if you are actually going to do that, then the equation you are going to get is u into dou u by dou x plus v into dou u by dou y is equal to minus 1 by rho dp dp infinity by dx minus g is actually coming because of the body forces, minus g plus nu into dou square u by dou y square. Okay, why here my dp infinity by dx is actually coming? Okay, so for flow over flat surface we actually discussed this. So on a flow over flat surface we said that dou p by dou y. Okay, so in that direction, in that case, it is actually going to be x, it is actually going to be y. Okay, always in the direction of a plate we are actually taking as x, direction perpendicular to the plate we are taking as y. Okay, in that case we said that dou p by dou y is equal to 0. That means velocity profile or velocity variation perpendicular to the plate was actually 0. Okay, and then we actually said that so therefore dp by dx is actually going to be there. Only dp by dx is actually going to be there. So instead of dou p by dou x, we could actually write dp by dx. Okay, since there is actually no variation in the y direction, it should be actually whatever the temperature variation, okay, or dp by dx inside the boundary layer, inside BL should be same as dp by dx outside boundary layer. Okay, so that's what we were actually discussing, right? So therefore, outside the boundary layer, dp by dx is equal to dp infinity by dx. Okay, so that's what we were actually saying. So therefore, here also we can actually see that. The direction perpendicular to that, it is actually y. So here also dou p by dou y is equal to 0. Okay, dou p by dou y is equal to 0. So therefore, whatever the dp by dx within the boundary layer should be actually equal to whatever the dp by dx outside the boundary layer also. That's why we have actually written here dp infinity by dx. So p infinity is actually the temperature profile outside. Just we can actually say. Okay. So therefore, yeah. So this one we are actually writing as 83. But can anyone say what is actually dp by dx outside? What is actually going to be dp by dx outside? Or what is actually pressure, say? What is actually the pressure at this point, infinity? Okay, suppose
Atmospheric pressures.
we can actually say atmospheric pressure, but just for sake, I'm actually saying this is actually at a height, say some x, okay, some h height we are actually saying. Okay, suppose we are actually talking about the total height, some reference we are actually saying as I don't know, some reference height is say h, and this one is actually at a distance h dash or something. Okay, so P infinity is therefore equal to, from the hydrostatic equation, it is equal to rho gh, right? In this case, it is going to be equal to rho g h minus h dash. Okay, so what I am actually saying is there is actually a variation of the pressure outside. Okay, there is actually going to be a variation of pressure outside due to the hydrostatic forces. Whether it is actually relevant or not, we cannot actually say. If it is a ambient condition, say if it is a fluid and all, common air and all, it is actually not that much. But if you are actually talking about a liquid outside, then it is actually going to be very high, right? So whatever we are actually going to show over here, it is not just a flat plate with air we are talking about. It is actually applicable for any neutronifier. It can be actually happening in the oceans, or it can be actually happening in a or in a pan on our stove. Okay, so everywhere this is actually going to be relevant. Okay, so therefore, what I'm actually saying is there is actually going to be a cytostatic forces. So therefore, we can actually say is that outside boundary layer dp infinity by dx we can actually write as minus rho infinity into g. Okay, so rho gh. So that's what it is actually going to come. So the p is actually vary due to the body forces. Okay, so that's what we can actually come up. So putting this into the previous equation, so you are actually going to get u into dou u by dou x plus v into dou u by dou y is equal to g into delta rho by rho. Okay, plus mu into dou square u by dou y square. Okay, so we are actually combining these two terms. Okay, we are combining the term 1 and term 2. Okay, so you can actually combine and you can actually write like this. But density is as it is, yeah, where delta rho is equal to rho infinity minus rho. Rho is the density within, and delta rho rho infinity is actually the rho infinity is the density outside, and symbol rho is actually the density within the boundary. Okay, so but the density as it is actually not helpful for us. So we need to actually use some methods to write density in terms of temperature. Okay, we are actually trying to convert the density in terms of temperature. So luckily for us, there is actually some term which is actually known as volumetric thermal expansion coefficient. Volumetric thermal expansion coefficient. Okay, that is actually beta. Beta is equal to defined as 1 by rho dou rho by dou t at a constant pressure. Okay, so beta is equal to minus 1 by rho dou rho by dou t at a constant pressure. We are just going to tweak this a little bit. Okay, so beta we are actually trying to write as minus 1 by rho. Okay, so in our particular case, if you are actually doing some scaling analysis, what you can actually write is delta rho as rho infinity minus rho divided by delta t as t infinity minus t. Okay, so that's what we are actually going to write. It is not equal to, it is similar to, that's it. Okay, so again, therefore we can actually write as rho infinity minus rho divided by rho is equal to beta into t infinity minus t. Okay, so this is actually a very big assumption. So this simplification, so we have actually converted the density ratio into beta into delta t. Okay, so this is actually a very big simplification. This simplification is known as Bose-Einstein approximation. This simplification is Bose-Einstein approximation. Bose-Einstein approximation. Okay, so therefore it actually reduces our reduces our equation greatly. But again, one issue is actually going to come that we will actually see now. So therefore, if we are actually going to solve this, the set of governing equation is actually going to be, obviously the mass transfer is actually going to be the mass conservation. So till now we actually discussed on momentum equations. Okay, so that is just a momentum equation we actually discussed. So we are going to write all the governing equation. Mass conservation is going to be there, which is dou u by dou x plus dou v by dou y is equal to 0. Okay, and next is actually the momentum is actually going to be there. Okay, x momentum X momentum going to be there, that is equal to dou u into dou u by dou x plus v into dou v by dou u by dou y is equal to, now we can write g beta T infinity minus T plus nu into dou square u by dou y square. Okay, and then energy equation. Energy equation going to be equal to u into dou T by dou x plus v into dou T by dou y is equal to alpha into dou square T by dou x square. Okay, yeah. So this is actually going to be the dou x square or dou y square. Okay, y square we can actually. Okay, so because x square along the length, we are actually neglecting. Okay, so therefore these are actually the set of governing equation, energy equation. But here you can actually see there is actually a very big trap over here. Even though it actually says symbol, in the momentum equation, the temperature comes into picture over here. Okay, it never happened in case of forced convection, right? It never happened in forced convection because, for example, in our flow in the cylinder, flow inside the tube, we actually said that we are actually getting some equations, and then we are actually putting our equation of U into the energy equation, and then we were actually getting the temperature profile T. Okay, so therefore we were actually very happy over there because everything was actually simple. First solve the momentum equation, get U, then solve the temperature equation using the velocity profile. But that is actually not going to happen over here, right? Because in order to solve the U itself, we need the temperature. In order to solve the U itself, the momentum equation itself, we need the temperature. Okay, so therefore we cannot actually solve it simply. We need to actually go for numerical methods only. Okay, with the numerical methods, you have to actually solve this, or you can actually go for some simplification and you can actually use some similarity solution also. That is also allowable. Okay, so some solutions are actually available. Okay? You can actually go through the textbook. It is actually given over there how we can actually go for these similarity solutions on. Okay. Yeah, so that is actually one thing. But again, we need to actually, if you're actually going to solve this full equation, then you need to actually go for, then you need to actually go for this numerical solutions, because the temperature dependent is actually there in the momentum equation itself. Okay. So if you are actually seeing again this, what about the beta? What about this thermal expansion coefficient? So beta for ideal gas, beta is equal to minus 1 by rho by rho T at constant pressure we are saying, right? But for ideal gas, we know P by rho is equal to RT. Okay, so based on that, you can actually get 1 by rho P by RT square, that is equal to 1 by T. Okay, so therefore for ideal gas, beta is equal to 1 by T. But for real gas, beta will be given. Okay, will be given or taken from take from table. Okay, so people have actually done the experiments, and they have actually developed the correlations for how beta is actually changing for ideal gases, and they have actually tabulated in the tables, and it is actually given in any textbook. Okay, so later we will try to do some solve some problems if at all. Yeah, then we can actually see how the beta is actually varying on. Okay, yeah. So that is actually it about the buoyancy or the free surface or a free convection. Okay, but still there is actually one more thing is actually pending on how we can actually decide where we are actually going with free convection or not. Okay, suppose the same wall we are actually going to have, and I am actually giving a small forced convection. Okay, I'm not going to give a very high forced convection, a small forced convection I am going to give, say U0. Okay, a small convection I am actually going to give U0. But again, here we are actually going to TS. Even though I am actually going to give an external convection, a thermal boundary layer, etc., are actually going to form, and the natural convection are still going to be there, right? If we are actually going for a vertical, the natural convections are still going to be there. Okay, I am giving a forced convection, and the natural convection is actually still going to be there. Then, therefore, we need to be actually knowing what kind of flow is actually dominant. Okay, whether the natural convection is dominant or forced convection is dominant, or if they are having the same effect on the flow, we need to actually know that. Okay, so that's what we are actually going to see, how we can actually say the relative effect of this natural convection as well as the forced convection. Okay, so we are actually going to define it in terms of a number called as Grashof number. Okay, for that we need to actually non-dimensionalize the governing equation, non-dimensionalizing the governing equation, dimensionalizing the governing equation. Okay, so we can actually say x star is equal to x by L, where L is actually some characteristic length, we don't know what. Okay, so y star is equal to y by L, and u star is equal to u by u0, some u0, some velocity, we don't know what kind of velocity we are talking about. V star is equal to v by u0. T star is equal to t minus t infinity divided by ts minus t infinity. Okay, where L is characteristic length, okay, L is characteristic length. Okay, it can be the height of it can be the height of the vertical plate, it can be the width of the vertical plate, it depends upon how you are actually defined. Okay, and u0 is a reference, is any a reference velocity. Okay, so we don't know what it is actually for now. Okay, because there is actually no u infinity is not going to be there. Okay, or incoming velocity is actually not going, might be actually there, we are not sure. So therefore we are actually just saying there is actually some reference velocity is actually going to be there, that's it. Okay, so now yeah, so likewise as we said, if there is actually a reference velocity, it is actually going to be there. So now we are actually going to non-dimensionalize it. So therefore we can actually see u star into dou u star by dou x star plus v star dou u star by dou y star is equal to g beta ts minus ts minus t infinity divided by u0 square into L into t star plus 1 by REL dou square u star by dou y star square. Okay, this is momentum equation. This is the non-dimensionalized momentum equation. Okay, so non-dimensionalized energy equation is actually going to be u star dou t star by dou x star plus v star dou t star by dou y star is equal to 1 by REL PR dou square t star by dou y star square. Okay, so this is actually the energy equation. Okay, where REL is equal to u0 L by me. Okay, so that is actually REL. Okay. So now here we are actually one particular term, g beta delta t into L divided by u0 square. Okay, so that particular term we are actually going to multiply by REL square. So then we are actually going to get the Grashof number. Okay, so we are actually saying Grashof number GRL is equal to g beta ts minus t infinity L cube divided by mu square. Okay, so that is actually going to be, or how it is we are getting is d beta Ts minus T infinity into L divided by u0 square into REL square, okay, into REL square. If you're actually going to do that, then you are actually going to get Grashof. Okay, so here you can actually see Grashof number. Grashof number is actually kind of the Reynolds number only that Grashof number is ratio of, what is actually its ratio? Here G beta delta T LQ. Okay, so that is actually going to be the buoyancy force divided by nu. Nu is actually the viscous force. Okay, like a Reynolds number is equal to inertia force to viscous force. So likewise, Grashof number is actually the ratio of buoyancy force to viscous force. Buoyancy force to viscous force. Okay, so definitely it actually tells us what is actually the effect of the buoyancy force. Okay, how strong the buoyancy force is actually going to be. Okay, how did we actually get that number? By non-dimensionalizing it. Okay, so that is Grashof number is actually therefore a very important parameter. But initially what we said is we need to actually get a relative idea of what is actually the buoyancy effect as well as what is actually the external effect. Okay, for that we can actually take this Grashof number buoyancy number ratio. Okay, if GR by REL square is almost equal to 1, then we can actually say buoyancy force, okay, almost equal to inertial force. Buoyancy force almost equal to inertial force. Okay, so in that case, free and forced convection must be considered. Okay, must be considered. When Grashof number divided by Reynolds number square is going to be much less than 1. Okay, much less than 1 means what? The buoyancy force is actually going to be much less than inertial force. Much less than inertial force. So in that case, only forced convection is considered. Only forced convection is considered. In that case, we can say Nusselt number is actually function of Reynolds number and Prandtl number. Okay, and similarly, Grashof number by Reynolds number square, if it is much higher than 1, then we can actually say buoyancy force is much higher than inertial force. Okay, so only buoyancy force is actually going to be there, or only free convection. Okay, only free convection. Okay, only free convection, and Nusselt number is actually function of Grashof number and Prandtl number. Okay, so that is actually the very basis of natural convection. I hope you got the idea and what is actually the parameter. So there is actually one more non-dimensional number which is actually Rayleigh number, which is equal to Grashof number divided by Grashof number by Prandtl number. Okay, so therefore, if you want, you can actually go through that. But this is actually the basic crux of natural convection. Okay, so by non-dimensional set, we are actually saying that a parameter which is actually the Grashof number is actually going to be important. Okay, so that's what I just wanted to mention for today. So we have actually successfully completed the convection as well as the boundary condition. Okay, convection as well as the free convection. Post convection and free convection we have actually. Okay, so from next class we can actually move on to the application of convection, which is actually the heat exchanger. Okay, so if you have any doubts, we can actually discuss now. Any doubt?
Yes, sir.
Any doubts, yes or no? No doubts.
No doubt, sir.
Okay. So if you are all free, if you have say half an hour, then we can actually discuss on this midsum exams also. Do you want to, or otherwise I can actually send a video or something. What do you actually want? Want to discuss now? Do you want to discuss the midsum papers? So otherwise, I will just send a recorded video, different recorded video. I will just send. I don't want to spend a class or time during our regular class. So I will just send yeah, maybe I will just send a recorded video discussing the answers, midsum answers, and also a tutorial. Also, I will actually send. Okay, go through the tutorial together with the solutions. I will actually send. Go through the tutorials also. Okay. Okay. Thank you. Thanks for coming. And I will share this video with all. Okay. Have a nice day to all.
Yes, sir.
Thank you, sir.